Hey guys, this is Mrs. Brookshire from Glenver High School, and today we're going to be discussing the language of experiments. So we're still in section 4.2. This is part 2, still talking about experiments. Some important things to consider when doing an experiment. This first box, there's some vocab here, so I'm going to read through it. If you need to stop, then do that and to copy it or pull up the filled in notes and you could copy it there as well. A specific condition applied to the individuals in an experiment is called a treatment. If an experiment has several explanatory variables, a treatment is a combination of specific values of these variables. An experimental unit is the object in which a treatment is randomly assigned. When experimental units are human beings, they're often called subjects. So I know that you've heard, doctors speak about, or people that are doing an experiment will say these subjects. So those are actually human beings that are being assigned some type of randomly assigned treatment. Okay, so we're going to look at the first problem. And it is talking about malaria causes hundreds of thousands of deaths each year, with many of the victims being children. Will regularly screening children for the malaria parasite and treating those who test positive reduce the proportion of children who develop the disease? Researchers worked with children in 101 schools in Kenya, randomly assigning half of the schools to receive regular screenings and follow-up treatments, and the remaining schools to receive no regular screening. Children at all 101 schools were tested for malaria at the end of the study. Identify the treatments in the experimental units in this experiment. So this is kind of going back to this vocab here. So obviously the treatments, there were 2 treatments. They were regular screenings and follow-up treatments. So that was one of them. So some of the schools that they chose, they did regular screenings and follow-up treatment. And then some of the schools they chose, there were no regular screening. Okay, so those were the 2 treatments. Each school got one or the other. Okay, what are the experimental units? It's the students in the 101 schools in Kenya. So it's the 101 schools in Kenya, basically. So that's what they were, the children in those schools. Okay. So the next vocab we're going to speak of is what's a factor. And in the experiment, we have a factor. That is an explanatory variable that is manipulated and may cause a change in the response variable. The different value of a factor are called levels. Okay. So in an experiment, a factor is an explanatory variable that is manipulated and can actually cause change in the response variable. And many times there's each factor has certain levels that it's using. So we're going to look at this one particular problem. Have you ever dropped a tasty piece of food on the ground and quickly picked it up and eaten it? If so, you probably thought about the 5-second rule, which states that a piece of food is safe to eat if it's been on the floor less than 5 seconds. The rule is based on the belief that bacteria need time to transfer from the floor to the food, but does it work? So they actually did this experiment at Rutgers. Researchers from Rutgers University put the 5-second rule to the test. They used 4 different types of food: watermelon bread, bread with butter, and gummy candy. They dropped the food onto 4 different surfaces: stainless steel, ceramic tile, wood, and carpet. And they waited for 4 different lengths of time. There was less than 1 second, 5 seconds, 30 seconds, and 300 seconds. Finally, they used bacteria prepared 2 different ways: in a tryptic soy broth or peptone buffer. Once the bacteria were ready, the researchers spread them out on the different surfaces and started dropping food. So what we're going to do is, in this particular problem, we're going to list the factors in the experiment and the number of levels for each factor. So let's do that first. So the factors were, you had 4 different types of food. So food was one of the factors. How many levels? There were 4 levels because there were 4 different kinds of food. The next one, there were various surfaces, types of surfaces. And there were 4 levels of that as well, because you had stainless steel, ceramic, tile, or wood, and carpet. Stainless steel, ceramic, tile, wood, carpet. Yeah, so there's 4. And then they waited for 4 different lengths of time, so amount of time was another factor. There were 4 levels. And finally, method of bacterial prep. And there were 2 levels of that. So, part B, if the researchers used every possible combination of levels to form the treatments, how many treatments were included in the experiment? Well, what you would do is some simple math here. You would multiply 4 times 4 times 4 times 2. And that would give you 128 different treatments. So you would get all the different combinations there. And then list 2 of the treatments. So what I did is I just went and picked one of these, one of these, one of these, and one of these, and then I did it again. So I picked watermelon, stainless steel, less than 1 second, tryptic soy broth. And then another one would be gummy candy, wood, 300 seconds, and Peptone buffer. Okay, so are you interested in what the researchers found out? Well, they discovered that wetter foods had greater bacterial transfer. They also found out that food dropped on carpet had the least bacterial transfer. The longer the food was on the surface, obviously there was greater bacterial transfer, although some transfer happened instantaneously. Overall, researchers concluded that the type of food and the type of surface were as important as the amount of time the food was on the surface. So that was a pretty interesting experiment there. Okay, so the next thing we're going to talk about is control group, which we've already talked a little bit about, I think, in this chapter. Many laboratory experiments use a design that is much too simple and can yield worthless results. So this is what the one that's not very effective would be, a very good experiment. You have experimental units, you impose a treatment, and then you measure your response. Okay, so very simplistic. Usually not good results. Okay, so in an experiment, a control group is used to provide a baseline for comparing the effects of other treatments. Depending on the purpose of the experiment, a control group may be given an inactive treatment or a placebo, an active treatment, or no treatment at all. So let's talk about, what does a control group do as far as an experiment. In an earlier example, we described an experiment in which researchers randomly assigned 101 schools in Kenya to either receive regular malaria screenings and follow-up treatments or to receive no regular screenings. Explain why it was necessary to include a control group of schools that didn't receive regular screenings. So let's think about why it would be important to have a control group in this experiment. Okay, so basically when I think about a control group, I think about it being sort of a baseline. Okay, so let's say the control group provides a baseline. The control group provides a baseline for comparing the effect of regular screenings and follow-up treatments. Okay, so the control group provides a baseline for comparing the effect of regular screenings and follow-up treatments. Otherwise, researchers wouldn't be able to determine if a decrease in malaria rates was due to the treatments or some other changes that occurred during the experiment. So that's why a control group is so important. So let's write without a control group, researchers wouldn't be able to determine if a decrease in malaria rates, those were malaria rates we were looking at, was due to the treatment or some other change that occurred during the experiment. So that's what that control group is for. Okay. So you can actually tell if there is a result based on the treatment or if it was due to some other change. Okay. All right, so there are two kinds of experiments, and these have to deal with who knows about the treatment. So a double-blind experiment, neither the subjects nor those who interact with them and measure the response variable know which treatment a subject is receiving. So the people getting the treatment or the people giving the treatment, neither know which subject's getting which treatment. Now, in a single blind experiment, either the subjects or the people who interact with them and measure the response variable don't know which treatment a subject is receiving. So one or the other. This one, neither know. This one of them doesn't know. Okay, so let's do a problem concerning double-blind treatments. Early research showed that magnetic fields affected living tissue in humans. Some doctors have begun to use magnets to treat patients with chronic pain. Scientists wondered if this type of therapy really worked. They designed a double-blind experiment to find out. A total of 50 patients with chronic pain were recruited for the study. A doctor identified a painful site on each patient and asked him to rate the pain on a scale of 0, which was mild pain, to 10, which is severe. Then the doctor selected a sealed envelope containing a magnet or at random from a box with a mixture of active and inactive magnets. The chosen magnet was applied to the site for 45 minutes. After being treated, each patient was again asked to rate the level of pain from 0 to 10. So explain what it means for this experiment to be double-blind and why is it important for this experiment to be double-blind. Okay, so double-blind, part A, would be neither the subjects nor the doctors. Neither the subjects nor the doctors. Applying the magnets and recording pain ratings knew which subjects had active or inactive magnets. So that's the meaning of double-blind in this experiment. Okay? Neither the subjects nor the doctors applying the magnets and recording the pain ratings knew which subjects had active or inactive magnets. Why is it important for this experiment to be double-blind? Okay. So if the subjects knew which treatment they were receiving, researchers wouldn't know if the improvement was due to the magnets or to the expectation of getting better. So if subjects knew treatments or treatment being imposed, researchers would not know if improvement was due to magnets or expectations of getting better. Because sometimes, I think expectations of getting better. I think if you take some medicine and you're going, oh, I feel better. Sometimes, you can actually talk yourself into, hey, I've got these magnets, so my pain is going to get better. So it's better to have a control group so you can actually figure if that is what's going on. Okay? And then if the doctors knew, they could possibly treat one group different from the other. If doctors knew which subjects received which treatments, they may treat one group differently than the other. They may treat one group differently than the other. Okay? So it's kind of like if they knew the ones that had the magnet treatment, they could ask questions differently. They could just treat them a little bit differently than the ones who they knew didn't have or had the inactive magnets. So that is why it's important to experiment for that one to be a double blind. Okay. Next problem. A new analysis is casting doubt on the claimed benefit of omega-3 fish oil. For years, doctors have been recommending eating fish and taking fish oil supplements to prevent heart disease. But the new analysis reviewed 20 previous studies and showed that the effects of omega-3 aren't as great as once suspected. One reason is that an early trial of omega-3 supplements was conducted as an open-label study. In this type of study, both patients and researchers know who's receiving which treatment. So this one, everybody knows. The subjects know, and the patients know, and then the researchers also know. So why is this a potential problem? I was thinking about this one, and sometimes, like if you were receiving the omega-3 fish oil, and it's supposed to improve your heart issues or heart disease or prevent heart disease. You could be like, okay, I'm taking this fish oil. It's supposed to make my heart, disease or prevent heart disease. So I think I'm going to go on and really exercise, or I'm going to eat healthier. And so if you knew that you were getting that and you did these other things, it's not really for sure that that's what was really helping you with the preventing heart disease. It could have been the other things. Whereas if you really didn't know, you might not try these other things to also help improve or prevent heart disease. So let's see what we could write. Patients and researchers who for some people, this knowledge would motivate them to take other measures that would also influence their heart health. So let's write that. So for some subjects, this knowledge could motivate them to take other measures, that would also influence their heart health. Part 2, describe how you can fix the problem identified up there. Okay, so you could use a double-blind experiment. At least use a single-blind experiment. Like, don't let the subjects know what they're doing. The patients wouldn't know which treatment they received, and the researchers would also not know. So let's just say the patients nor researchers would know which treatment they received. Which might prevent some of this happening. Okay. When you are designing an experiment, you want to have random assignment. Okay, so what that means is, in an experiment, random assignment means that the experimental units are assigned to treatments using a chance process. And we have talked a lot about this in this chapter. How do you assign? It's kind of like if you were to do a sample, it's the same idea. Like, how do you, what are the different ways that you could, assign treatments? And it's, like I said, similar to ways we maybe would have done a survey earlier in this chapter. So it says a total of 20 students have agreed to participate in an experiment comparing the effects of caffeinated cola and caffeine-free cola on pulse rates. Describe how you would randomly assign 10 students to each of the two treatments. Okay, so we're going to go through and talk about each one. So using 20 identical slips of paper, there could be other, this is what I was thinking about this one. So take on 20 identical slips of paper, write A on 10 of the slips and B on the remaining slips. Put the slips of paper in a hat or a box. Mix thoroughly. Hand a slip of paper to each volunteer, or you could let them choose a piece of paper out of the hat or the box. And then students with A would receive cola with caffeine, and students who get a B slip would receive cola without caffeine. So that would be one way you could randomly assign treatments is by using kind of like an SRS there, okay? So it's kind of the same idea. So one way would be to use the slips of paper. Okay? Another way would be to use your technology, your RandInt on your calculator, random integer on your calculator. So what I thought about doing is to assign each of the 20 people a number from 0, 1 to 20. And then you could, the first 10 people that you get a different integer between 0, 1, and 20, you could assign them. So I said label each student 1 to 20. Oh, okay, 1 to 20, because if we're doing RandInt on the calculator, just 1 to 20. And then randomly generate 10 numbers, the students with these 10 numbers. So the first 10 that you get receive cola with caffeine, and then the remaining 10 would receive cola without caffeine. So, let's see, push that up, sorry about that. So label each student 1 to 20, randomly generate 10 numbers. The students with these 10 numbers receive cola with caffeine, the other 10 receive cola without caffeine. And then the random digit table, using the table D or random digit table. This is the one where you would number the people from 0, 1 to 20. And you would go through, pick a line, label each student with a digit 0, 1 to 20, go to a line on a random integer table, and read 2-digit numbers moving left to right. Assign cola with caffeine to the first 10 different numbers, 0, 1 to 20, and the remaining 10 would receive cola without caffeine. So those are there's 3 different ways that you could randomly assign 2 treatments. And you want to kind of spell it out, like exactly what you're going to do. And this kind of does to me, like we talked about these kinds of random, this is an assignment, but we've also talked about this in the sense of like if you were doing a survey, these methods were used. And that does it for the experiments. I will be talking to you. We're getting ready to start the next section, which would be section 4.3, part 1. So I will be with you on that next section as well. Talk to you later.